Hey guys, welcome to another video. Today we're going to be going through the topic of pressure. So here we've got a few things that we want to cover today, so have a read through that before we begin. So quite simply, pressure is the force exerted per unit area. You've got here in this diagram an exemplification of the force, a block of force acting on a certain area, and the pressure is force divided by the area. Force is in newtons and area is a meter squared, and naturally pressure, the units for it, is newtons per meter squared. So a very important formula. Now, one way that we can measure air pressure or atmospheric pressure is using the Mercury Barometer, and there's a few important concepts that we have to go through with this, but let's just think about how the Mercury Barometer actually works. You've got the mercury inside this setup. Some of the mercury is exposed to the air, and it's going to cause air molecules to collide against the surface of the mercury here, right? And what that will do is cause a downwards force, or the air pressure is going to push the mercury downwards. And when that happens, the mercury that's inside this column tube here will go upwards naturally, as you might expect, and the space here in the tube, it's completely vacuum. You might have a few little vaporized mercury molecules sitting inside this chamber, but for the most part it's vacuum. Okay, and so obviously the stronger the air pressure, the more higher up the mercury will go in this column. And we can actually calculate the air pressure after the height has stabilized inside the column by utilizing the concept of pressure that's exerted beneath a liquid surface. Okay, so let me just take you to this whiteboard here. I want you to imagine a big block, a big container, right? Now, in this container, you have water, like this. Okay? All of that stuff is water. And so if you think about it, if you were standing up here, well, you wouldn't feel any pressure from the water, right? Because, there's no water above you or anything like that. But imagine if you were right down here. What you'll feel is the pressure of the water above you. This entire block is pressing down against you. Okay? And the reason that happens is because water molecules have a density, and you've got the gravity that's pressing down against you. And obviously water has a mass and everything, which is, part of density. But ultimately speaking, the concept that I want you to get aware of is that when you are beneath a certain extent of the surface of the liquid, then that bulk of the liquid that is above you is gonna exert pressure against you, right? And that's exactly what we're talking about when we talk about the Mercury Barometer here. So if you place the Mercury Barometer outside, it's going to the air pressure is going to press against this surface here, and it's going to push the mercury upwards, and eventually it'll come to an equilibrium where the height has stabilized inside this column. Okay, and so what we can do then is, what we know at this point in equilibrium is that this downwards force, pressure, so atmospheric pressure, is actually at this point the same as the downwards pressure exerted by the column of mercury here. So you've got the height of the mercury right here, and just like we talked about with you standing at the very bottom of this column of water, if you calculate the pressure right down at the bottom here, at the base of the column, that's the pressure of the mercury column. Okay? And for this height to be stable and for this to be in equilibrium, what it means is that the atmospheric pressure is equal to the pressure caused by the mercury column. And that makes sense because otherwise the height would change. For example, if I suddenly amplified the pressure and, times it by 5, suddenly increasing the atmospheric pressure, then what you'll find is that it'll break the equilibrium and you'll start to find that the mercury will start to rise inside the column. And obviously that would decrease down like that because you're increasing the pressure and more downwards force will cause that to happen. But given that everything is in equilibrium, then what you know is that the atmospheric pressure must be equal to the pressure inside the mercury column. So, given that to be the case, in order for us to calculate the atmospheric pressure, all we need to do is calculate what the pressure is at the base of this mercury column, which we use the formula ρgh. And what rho is the density of the material, in this case the density of the mercury. Gravity is g, and the height is the height of the mercury column. And in fact, this doesn't apply only to this certain experiment. This formula ρgh calculates the pressure that is exerted beneath any liquid surface. So you can still use this formula, for example, if you were underneath the sea and you're like right here and you've got a height of, let's say, 10 meters, you've got the density of water being a certain amount, then yes, you can calculate the amount of pressure exerted like that as well. But for this particular example, we're going to be looking at strictly the mercury barometer because that's the focus of our thing today. So here, the pressure beneath the liquid surface is equivalent to ρgh, and you've got the density, you've got the gravity, and you've got the height. So let's actually go through an example here. You've got the density of mercury being 1.4 times 10 to the power 4. And so figure 3.1 shows that an experiment is used to determine the atmospheric pressure. And remember, you've got the atmospheric pressure pressing against here, but you've also got the pressure of the mercury going down here, and you've got the pressure point right at the base here, which is the pressure of mercury. And so we know that in equilibrium, pressure of atmosphere is equal to the pressure of mercury at the base of the column, which is of course equal to ρgh, and we'll be using that in a second. So the name of the instrument is obviously the Mercury Barometer, and the space A has a vacuum in it, as I said before, which is the space here. Now calculate atmospheric pressure. Well, PATM equals ρgh. We know that ρ, or the density, is 1.4 times 10 to the power 4. We know that gravity is 10, and we know that the height is 760 millimeters. But we want to convert that into meters. So if you divide that by 1,000, you got 0.76. And so therefore, when you calculate that, you get 1.1 times 10 to the power of 5 pascals. Okay, so I hope that makes sense for you. Now, when we want to measure the pressure of a gas, we can use the setup called the manometer, which is actually sort of very similar to the barometer, but essentially what you do is you have a gas whose pressure you want to measure, and it enters through this tube here. Now, as it enters through that tube, it's going to exert some sort of pressure against the liquid surface that you see over here. And on the other end, in this U-shaped setup, you have just open tube, which is exposed to the air. And the air will exert some sort of pressure on the liquid. And what we're trying to do is sort of see what the difference is in height between left and right. Okay? So just have a little think about this. Let's take you back to this whiteboard. If you've got this U-shaped setup here, right? And let's just imagine that you don't have any extra gas coming in, like you've just got air and air. Then what do you think would be the levels of each of these two different tubes? Well, given that the air pressure is the same on both sides, you're going to have an exactly level height between the two tubes, right? So the height difference is going to be 0. But let's just imagine that you've got, this time you're going to have gas, and again, of course, this one's going to be air. And we're just going to imagine that the pressure of the gas is higher than the pressure of the air. Then what do you think will happen in terms of the height differences between these two tubes? Well, as you might expect, the stronger pressured gas is going to force the liquid down more than the less pressured gas. So in this case, if we're assuming that this gas on the left-hand side has a higher pressure than air pressure, what you'll find is the height levels might look something like this. Right? Because there's more force being exerted here than here. And oppositely, one more scenario that you might get is, of course, when the gas that you put in on the left-hand side is less stronger than air pressure. In which case, you'll find the opposite to be the case. Because air is exerting more pressure than the gas itself, then you'll have a setup like this, where the height of the gas side is going to be higher than the height of the air side. And this height difference is extremely important. And I want you to listen very carefully here, because what we're going to say is that when you have the pressure of the gas being higher than the pressure of the air, in other words, when you have the mercury, or whatever liquid it is, lower on the gas side than the air side, we're going to say that it's positive height. So when we calculate the height, we're going to use a positive number. But when the gas pressure is lower than the air pressure, or in other words, when you have the liquid being higher on the gas side than the air side, we're going to use negative height. Okay? So even if the heights were both 10 millimeters, in this example it'd be 10 millimeters as normal, but here it would be minus 10 millimeters. And you'll see why this is relevant in a second, but in fact, you know, just be aware of that, and we'll go through some questions in a second. But here, the pressure due to the gas, the formula we're going to use is atmosphere plus rho gh, and h being the difference in the heights between the two tubes. Okay, so let's have a look at that. Here they say that a U-shaped tube of constant cross-sectional area contains water of density 1000. Okay, both sides of the U-tube are open to the atmosphere. So the atmospheric pressure is 1 times 10 to the power 5 pascals. The left-hand side of the tube is now connected to a gas supply using a length of rubber tubing. This causes the level of the water in the left-hand side of the tube to drop by 0.2 meters as shown in figure 3.2. Calculate the pressure of the gas supply. Give your answer in 3 significant figures. Okay. Well, the first thing we're going to do is analyze the situation. Well, you've got the gas coming in from the top here. Now, is the gas stronger or weaker than air pressure? That's gas. That's air. Well, you know that this is lower than this. So this gas must be stronger than air. Now, what we want to do is calculate the difference in height. Now, remember, if this is 0.2 meters, then this must be 0.2 meters. And the total difference between the heights is 0.4 meters. Okay? And so what we're going to do is put that into the formula. So pressure of gas equals atmosphere plus rho GH. So atmosphere is 1.00 times 10 to the power 5. You add that to rho, which is 1000. Get rid of that. Gravity. Oops. Sorry. I'm just going to see if I can get rid of that. So density again is 1000. Multiplied by gravity. And then multiply that by the height, which is what? 0.4. And so when you do the calculations, you get 1.04 times 10 to the power of 5 as the pressure. And you can see why the sign that you put in front of the height matters, right? Because I want you to consider another example where you might have had the opposite situation, where you have something like this. And let's just say the height difference here was 0.4 meters as well. But if you were to think about it, right? If you just plug that into the formula without doing anything, right? Without changing the sign to a minus 0.4 meters, then you'll get the same result, 1.04 times 10 to the power 5. As the pressure of gas. But that can't be true because we know for a fact that air pressure is higher than the gas pressure here. Remember, gas is coming this way and air is coming this way. But given that the level of the fluid is lower here than here, the air pressure must be stronger than the gas pressure. But we know that the atmospheric pressure is actually 1.00 times 10 to the power 5. So whatever pressure we get for the gas must be less than this amount in this situation. But if we calculate the 0.4 meters without putting the minus sign in front of it, then you'll get 1.04, which is clearly wrong. So that's why it's important that for you to do the calculations of pressure of gas equals atmosphere plus rho GH, this H, in this case, if you did it properly and put minus 0.4 meters, then you'll get the right answer, because then that will become the same as atmosphere minus rho GH. So then what you'll get is an answer that is less than the atmospheric pressure, which is correct. Okay, so the thing I want to demonstrate is just make sure that you appropriately put the correct sign in front of the height when you do this calculation using this formula. Otherwise you might get the wrong answer, but also just use your conceptual awareness as well, and when you arrive at an answer, just make sure, okay, well, do I know that the gas is lower or higher than the air pressure just by looking at the liquid levels, and then just sort of go from there. So I hope that video helped, guys, and we're finally at the end of general physics, and we'll be moving on to some other stuff like waves in the next segment. free resources on Free Exam Academy, just notes and things like that for IGCSE biology, chemistry, and physics. And please check out my Patreon channel as well. Not a lot of physics content at the moment, but I will be going through a lot of past paper stuff there eventually on physics, but I've got a lot of it already on chemistry and biology, so make sure you check that out, and I will see you in the next video.